So we're going to keep going with the U2A7 measures of variability of data part 2. So this one, a little more meat to this than the last activity. First things, I want to just show you this right here. Absolute value. If you've never seen this before, what an absolute value symbol is, first, let's get the symbol down, so let's go to green, is this sort of thing here, two straight lines around a number or a variable, okay? And what this means is, let's get rid of the sign involved, okay? So it's the size of the number. So if I have this, remember number lines, if I had 3, I go 1, 2, 3 in that direction. If I had -3, I'd say, let's go 1, 2, 3 in that direction. These are vector quantities. They have a size and a direction, okay? A scalar quantity has no direction, and that's what's going on with when we talk about absolute values. We kind of change a vector quantity into a scalar quantity. We don't care about the direction, we care about the size. So every single number will just have a positive sign. So the absolute value of 5 is 5, the absolute value of -15 is 15. Just get rid of the sign. We don't care about the sign, we care about the size of it, okay? And there's more questions there, but that's the general gist of it. Once we get going now, we talk about the deviation and what is called standard deviation. Is the main thing. Okay, so we're going to start off here with the average deviation from the mean. So what you're going to do here is we're going to get the mean, and for each point, we're going to figure out how far they are from the mean. So there's a bunch of data, and we're going to work our way through this. And when we talk about average deviation from the mean, okay, we are looking at the absolute value of the deviation. Okay, so here's the mean. Okay, and we have all these points. There's one over here, another one over here, another one over here, and we're gonna figure out what is the deviation from the mean on average. How far away are the points on average from the average? Okay, so the average deviation from the mean, which is the average. Okay, so we figure out the mean, and in this case it was 67, and then we get all our points, and we say 70 subtract 67 is 3. Okay, and we only care about the size of it, not the sign, okay? Because here is the point, okay? So let's say we have some data in 67, and my 1 point is 70 away from the average, okay? It's 3 away, sorry, my 1 point is 70, which is 3 away from the average. Well, a point of 64 is also 3 away from the average, okay? When we talk about the average deviation, if we average these out with the sign, then we would say, look, that's -3, that's 3, they equal to be 0. And I think we had that we showed that yesterday with yesterday's note, okay? So we don't care about the size of it, we care about this, we don't care about the sign, we care about the size. So get the deviation, cut out the signs, that becomes a positive, that becomes a positive, the other ones are all positive, add them all together and divide by the number of, so the 6 is that there were 6 pieces of data. Okay, so 1, 2, 3, 4, 5, 6, and the average deviation is 433. Okay, so it shows something kind of interesting. It shows on average how far you are from the mean. So what's the context here? Let's go back to the question and figure out what this means. 6 months stack value of banana computers are as this. The average deviation for the mean. So I don't even know what that question actually means. But let's pretend this is how much you earned each month. Okay, you had a job and you earned that amount per month. Okay, and then you figure out, look, my average is 67. That's great. Okay, but now I have a deviation on average of $4.33 one way or the other from 67. So on average, I can be $4.33 this way or $4.33 this way. Okay, and that's good. The bigger deviation, okay, the bigger the spread on average. Okay, so if my median was 67 and instead of 433, I had 933, well then I would know that what I'm making per month is a lot more varied than the guy who had 433. Okay, and that's what we're talking about. We're talking about spread of data now, not the central tendency as much, but how spread they are. This is the big one here. Standard deviation and variance, they go together. And what we're going to do is figure out the standard deviation and the variance for data. Okay, so this here you may have seen in the past. A lot of you will not have seen it. It's part of the grade 11 college curriculum. You may have seen it in grade 10 academic math. You probably did not see it in either the grade 11 university or the grade 11 mixed course. So a little bit strange that that's the case. But so it's been a year or two since you've seen it, if you've seen it at all. So what we're going to do here is look at the sample or the population variance. So that's going to be another measurement of spread. So okay, so why do we care about this? Well, if we have a bunch of data, right? So if I measured something, and let's say how much money I made per month. and it was $66, $66, $66. And I look at this and I say, what's the mean, median, mode? I would go 66, 66, 66. Okay. Now, if another guy comes back and goes, oh, I earned $66, I earned $66, and then I earned $99, which is 33 more, and then I earned $33, which is 33 more, and I said, okay, tell me about this data. Well, what's the mean? Well, add them up, divide by 4, you get 66. What's the median? What's the middle? Well, 66 and 66 are in the middle. The average of these two is 66. What's the mode? What's the most common? Well, 66. Now, is this the same group of data as this? No, it's not. Okay, this is way more spread out. So to figure out how spread it is, one thing we could do, we've looked at, is the ranges, the interquartile range. We've looked at the box and whisker plots and all that stuff. But another thing you can look at is what we call variance or standard deviation. Okay, so this is variance. Now, in the past, when we talked about the difference between finding the average and a bunch of different things for sample and population, they were essentially the same work, right? So when we were looking at the mean, and I said, don't really worry about the fact that there's a little n versus a big N. Now, there is a difference here now. The data, there's a slight difference here. This sort of thing is still the same. So we're still kind of figuring out the difference between each point in the mean, which we'll get to in a second, and we'll square it. But there is a slightly different equation here. So for sample data, you have n minus 1, and for population data, you have the big N, okay, not minus 1. Okay, so it's the number of pieces of data in both cases, but here we subtract 1, here we don't. So you got to remember that, okay? If it's grouped by frequency, again, so we look at group by frequency, what you're going to do here is basically the same thing we did before, but again, you notice that there's a minus 1 with the sample. And again, when you look at class intervals, when you want to get the average in the class intervals, so with the data is in pieces like 30 to 40, 40 to 50, and that sort of thing, you're going to, again, use minus 1. So again, sample, you're going to have minus 1. Population, you'll have just the number of pieces of data. Okay, so standard deviation is the square root of the variance. So they go hand in hand, and we'll talk more about what they are later. But just know that basically here is your standard deviation, and that is the square root of the variance. Okay, so s squared or sigma. That's remember we were talking about sigmas. That's middle sigma. This is s squared. Depending on, and again, they are slightly different. That is for a sample. This is for a population. Same thing. We call them standard deviation here. That standard deviation. You don't change that, but they are represented by slightly different symbols. Okay, so let's look at this. How do you get this? How do you get the standard deviation and the variance? You take each piece of data. So we'll go back to you go back and check out that data that you had earlier with the mean of 67. You go and you figure out the mean, and then you take each point, and then you say to yourself, how far is each point from the mean? And then you square that. Okay, so slightly different than what we had the average deviation. Okay, this is standard deviation. So you'll take 70, subtract 67, and then square it, and then take 62, subtract 67, and square it. And you'll take all these things and you'll square them. And again, you're dividing by the number of observations. Now, in this case, it's a population. Okay, so I don't need the minus 1. I took all the data. Okay, the question will tell you, is it a sample, is it a population, and then you'll adjust this accordingly. Okay, so this would be 6 minus 1 if it was not a population. So now we get 70 minus 67 is 3 squared. That's 9. Okay, so you take all these and you square them. You can kind of ignore the negative at this point because when you square it, it becomes positive anyway. So you go ahead and you take all this stuff and you add them. So you get each of these, the difference squared, the difference squared, the difference squared, divide by 6, and you end up here with 25.3. Okay, that's going to be your variance. And now to get the standard deviation, you just take the square root of 25.3, which is 5.03. What does that mean? We'll talk about that later. But what it really means is this. The smaller the standard deviation, the smaller the variance, the more clustered the data is. So when we went back to all those 66 things and the 66 and the 99, oops, we had 99 and 33. Okay, let's just add another one here. So we have 4 pieces of data for each. That was kind of bugging me. This guy here will have a bigger standard deviation and a bigger variance, okay, than this guy here. And the bigger the standard deviation, the bigger the spread of the data. So if we plotted this, it would look like this. If we plotted this, it would look like this. Okay, we'd have 66 and 33. And once we start putting curves in, which we will, you'll notice these curves will be a lot tighter than the wider curves that have a higher standard deviation. Okay, so right now, kind of focus on how to calculate this. Okay, let's keep going now. This one's cut off, unfortunately. But you can go through this here and figure out what the standard deviation and the mean for these two guys are. Okay, so here you get the mean for both of them, and then you're going to figure out, so there's the mean, and then for each piece of data, you're going to subtract it. Now, one thing I want to show here is we're looking at here, that was population data. Now we're going to calculate, I'm sorry, this one here, this is going to be a sample of their work here. Okay, so they recorded how many trees they planted in each hour the following data was obtained. Now, how do you know it's a sample data and not population data? You read the question, and I think this is a great explanation here. It's sample data because it's only for 6 hours. This is how many trees they planted in each hour. Now, unless they work 6 hours in total, then this will be a sample of their work, okay? And the difference here is not in calculating the mean. Be careful here. You're not going to subtract 1 when you calculate the mean. Don't do that, okay? But when you get to standard deviation and variance, you are going to have to subtract 1 in here, okay? And that will be the only difference between what I did earlier and this here. So go over this, see if you get confused by that. It should be that difficult. Once you get frequency tables, it gets a little more annoying, to tell you the truth, okay? So you find out the mean, and then you find out the variance this way. Now, where it gets annoying kind of is, this isn't that bad actually. This is the same as saying I have one person 20, 25, 25, 25, 25, no 30s at a 35. So that's get the standard deviation of this data, okay? So it's not bad. And tell you the truth, if these numbers were a lot bigger, like if you have bigger frequencies like 31 of these and 44 of these and 106 of these and 19 of these, it would be a pain to write all this data out. So where it gets a little nicer is when you calculate, when you have a big piece of data like that, the only thing you have to throw in here is to multiply by the frequency. So you get the standard deviation of each point of data. Okay, so what's happening here is, let's look at the 25s, for example. For each of these, if I wrote this out each time, I would go 25, subtract the mean, squared. And I would do that 4 different times. So instead of doing that 4 different times, I just multiply by 4. It's the same calculation 4 times. Okay, and then I had none of these, so that kind of works its way out. And then just be careful, because it is, again, a sample data, piece of sample data, you're going to subtract 1 here. Okay, so if you get confused with the sample and the population, remember, are you looking at everything, or are you just looking at a chunk or a snapshot of something? If you're looking at a snapshot, it's a sample, not the population. And then you work your way through, and you get the sample data standard deviation. Sorry, kind of got a little bit lost there. Now, the only other thing you want to do here, the difference when it comes down to this, is the class interval stuff. When you want to find out the sample data for that and the variance for that, the variance or the standard deviation for that, all you're going to have to do here is, when you talk about the data, what's the data? It's between 10 and 20. 10 and 20. Let's just use 15. Okay, and then this is 25, and this is 35. We just kind of take the average. We take the midpoint of these. Okay, and I know it says 50 to under 60. This is good enough. Okay, so 55, and now it's just a frequency table. So you go back and you do it the same way you did the previous question. Okay, so you find you find the mean, then you subtract 15 from the mean. So you go 15 subtract mean, and you'll square it, but you have 3 of these. Okay, and then add to that 25 subtract mean, square it, and then you say you have 10 of these. Okay, and then you go ahead and you add those together, divide by 6, divide by the number of things here. And if this is population data, then you will not subtract. So here we have 3, 13, 21, and 4 is 25. So this would be 25, not 25, subtract 1. Okay, and that'll get you your variance. Take the square root of the whole thing and you get your standard deviation. Okay, so just work on that. It's a bit arduous. It's a bit tedious, but work on that today on calculating that, and then we'll talk more. It'll come up as the course progresses. What does that mean? Just know, though, that bigger standard deviation equal bigger variance. Okay, so if you have a bigger number, so if I have 66 and I have 22, that's bigger when I take the square root of each to get the standard deviation. This will still be bigger. So bigger variance, smaller variance, bigger standard deviation, smaller standard deviation. That means more spread out, less spread out. Okay, and then that will help you understand the data when we interpret it. Okay, so hopefully that it wasn't too much. Try some of the homework and give it a shot, and send me an email if you have any questions. Okay, take care.